Chapter 4 is about the combination between liquid chromatography and mass spectrometry. In the first part, we'll learn about mass spectrometry and later on the combination or hyphenation, as it is also called, with liquid chromatography. Liquid chromatography mass spectrometry, also abbreviated LC-MS, is probably the most widely used method in bioanalysis to date. This is because of the combination of separation of molecules according to their physicochemical properties, depending on the stationary phase, as you already know from previous lectures, and the separation of the generated ions according to their mass-to-charge ratio in the gas phase by mass spectrometry. As both properties are not related, we speak about so-called orthogonal separation methods. Mass spectrometry has quite a history, as you can see from this overview. Already in 1886, Eugen Goldstein discovered the so-called Kanalstrahlen or channel rays. In a gas discharge lamp, he saw that particles were formed that were traveling through the holes in the cathode straight on. That means that these particles had some inertia. Later it was shown that this was the first description of ions, and this was the basis of mass spectrometry. Wien later on showed that these channel rays or particles in the channel rays can be deflected by electric and magnetic fields according to their mass-to-charge ratio. This is the basis of the currently used mass analyzers. Ions are separated according to their mass-to-charge ratio, either in electric, magnetic fields or a combination thereof. Thomson later on constructed the first mass spectrograph, as he called it, by applying reduced pressure, vacuum, which is very important for mass spectrometry, and thus analyzing ions according to their mass-to-charge ratio. Anderson later on applied this to peptides and amino acids, maybe the first application to what we might call to date bioanalysis, biological molecules analyzed by mass spectrometry in this case. 1989. The Nobel Prize in physics was awarded to Hans Dehmelt and Wolfgang Paul for the development of the ion trap technique, the Quadrupole ion trap mass analyzer, which we will hear more later on. Finally, in 2002, another Nobel Prize, this time in chemistry, was awarded to John Bennett Fenn for the discovery of electrospray ionization, a very important technique that we will hear about, and to Koichi Tanaka for the discovery of soft laser desorption, SLD, of which we will hear a derivative which we call matrix-assisted laser desorption ionization, or MALDI. These two ionization techniques have been instrumental for the analysis of large biological molecules. This slide shows a picture of Eugen Goldstein's gas discharge tube. Note the rays behind the cathode. This is due to ions passing through the holes in the cathode after acceleration in a strong electric field. Later experiments showed by deflection in the magnetic field that these particles, or ions as we know now, are about 1840 times heavier than an electron. Every gas contains a low amount of ions initially due to cosmic radiation. These ions are then accelerated and collide with gas atoms, generating more ions by knocking off electrons. Ultimately, this leads to many excited ions that are accelerated, pass through the cathode, and emit their energy partially in the form of fluorescence. This can be then seen as the so-called Kanalstrahlen or channel rays. The first mass spectrometer was developed by Thomson, as mentioned earlier. However, only in the 1940s was mass spectrometry practically applied to petroleum fractions. This was based on a magnetic sector mass analyzer. In such a mass analyzer, ions are separated according to their mass-to-charge ratio in a magnetic field based on the Lorentz force. You may remember the Lorentz force from your physics lessons in school. In 1975 the Quadrupole mass analyzer was developed, which we will hear about a little bit more later on. It's a very important and widely used mass analyzer, and as mentioned before, the concept was honored with the Nobel Prize in Physics later on. Originally, mass spectrometry was coupled to gas chromatography, which was quite logical, since ions had to be in the gas phase for the mass analyzers to work. So it was logical to use gas chromatography where molecules are already in the gas phase and couple it to mass spectrometry. This is still an important technique to date. Only briefly afterwards, the first couplings of liquid chromatography to mass spectrometry were realized. This was much more difficult, as ions had to be transported from the liquid phase to the gas phase and then into a high vacuum. We will hear later on more about the challenges of coupling liquid chromatography to mass spectrometry. However, with the advent of new ionization techniques such as electrospray, this has become quite a routine method to date, and liquid chromatography mass spectrometry is the main and most important method in bioanalysis. Around the same time, physicists developed the Fourier transform ion cyclotron resonance mass analyzer. Here, ions are trapped in a very strong magnetic field of a superconducting magnet. This magnet has to be cooled with liquid helium to remain in the superconducting regime. Ions circulate in this magnetic field according to their mass-to-charge ratio and give certain resonance frequencies. We will not allude to this mass analyzer very much, as it is not really used in bioanalysis. It's difficult to handle and fairly expensive to operate. 1982 saw the advent of a very important mass analyzer, the quadrupole ion trap. The interesting feature of an ion trap is that ions are trapped in a kind of curved quadrupole. So you can trap a certain number of ions, and then you can do gas phase chemistry with these ions, for example fragment them into pieces or react them with other ions. An important feature of the ion trap is that it is a very small mass analyzer, and with recent developments the first portable mass spectrometers contain ion trap mass analyzers. In 1989 saw the advent of the time-of-flight mass analyzer, a completely different concept. Here essentially the flight time of ions is measured, and this flight time is related to their mass-to-charge ratio, as we will see later on. The interesting feature of the time-of-flight mass analyzer is that it is not limited by the mass-to-charge ratio, so you can use it to measure the mass-to-charge ratio of very heavy ions, such as those derived from biopolymers like proteins. In 1995 the ion trap was further developed to work with liquid chromatography mass spectrometry, and it remains one of the most important mass analyzers for this hyphenated technique. 2005 saw the advent of yet another mass analyzer that's very important today, the so-called Orbitrap. The Fourier transform Orbitrap ions circulate around a bottle-shaped electrode, and this mass analyzer also allows to achieve very high resolution, as we will see later on. We've already heard about some applications of mass spectrometry and liquid chromatography mass spectrometry in bioanalysis. But what are the general applications of mass spectrometry? What can you do with it? Very important is you can elucidate structures of unknown compounds based on their mass spectra. Not only the molecular mass, but also the fragmentation of these molecules into well-defined fragments, and the analysis of these fragments can sometimes lead to structure elucidation of unknown compounds. However, this is not an easy task. More straightforward is the confirmation of the structure of known compounds. This sounds kind of straightforward, but is certainly not easy in bioanalysis, where we are dealing with millions of compounds in one sample, and we would like to analyze just one particular compound, for example a drug or a drug metabolite. However, we know the structure of this drug molecule, and we can thus optimize our mass spectrometric method to focus on this molecule. An interesting application is the identification of compounds by searching a spectral library or database. We will hear about this in the field of protein analysis, but also small molecule analysis uses spectral libraries. This means essentially that the experimental spectrum is compared with thousands or even hundreds of thousands of spectra collected in a library online via the computer. A very important application for the bioanalysis is the quantification of compounds. In bioanalysis, we are generally not only interested in whether a compound is there or not, but we would like to know its concentration. To this end, we need to translate our signal from the mass spectrometer into a concentration, and this is done through the calibration with internal standards. More on the research side, the chemistry side, we can monitor reactions, either biochemical or chemical reactions. We can study the transformation of substrates to products by enzymes, but we could also study the fundamentals of chemical reactions in a mechanistic sense. Studying complexes and supramolecular assemblies is a recent use of mass spectrometry. It was long time thought of that it was not possible to study non-covalent supramolecular assemblies. However, if conditions are chosen and the ionization process is gentle enough, one can even bring complete viruses into the mass spectrometer, collect them on a plate, and after that infect mammalian cells with these viruses. Let's thus look very briefly into the main components of a mass spectrometer. It actually looks quite simple. First of all, you need to introduce your sample into the mass spectrometer. This is often not considered part of the mass spectrometer as such. This could be a simple syringe pump, an injection valve, or, in our case, mostly a liquid chromatograph. Then ions must be formed, because mass spectrometers can only work with molecules that are ionized. These ions must be in the gas phase and then transported into the high vacuum region of the mass analyzer. The mass analyzer performs the M/C separation, the separation of the ions according to their mass-to-charge ratio. Finally, we must detect the ions that have been separated. So the ions will hit a detector and generate an electric signal that is measured. This signal should be proportional to the number of ions. It's kind of an ion counter. However, in order to quantify molecules, we obviously need to calibrate the instrument. We need to know how many ions correspond to which concentration of the molecule in the sample, because none of these processes is 100%. Ionization may only be a few percent. We lose ions during the transport and in the mass analyzer, and also the detector does not give a signal for every ion that hits. Finally, again somewhat outside the actual mass spectrometer, is the data analysis part. That means the software, the computers that are needed to interpret the spectra and also to turn the mass spectrometry raw data into data that we can use to take decisions, such as in clinical chemistry looking at the concentration, for example, of a biomarker. Here you see a typical mass spectrum, actually a schematic of a mass spectrum. Let's look at the axis. The x-axis shows the mass-to-charge ratio, M/Z. The y-axis shows the ion abundance, or sometimes called the total ion current. In this spectrum we see different peaks which are non-assigned in this case. These could be three different molecules with different mass-to-charge ratios, but it could also be fragments of the same molecule, a molecule that broke, for example, during the ionization process. Interestingly, at each part we see a cluster of peaks. 2 peaks on the right, 3 peaks in the middle, and 2 peaks on the left. These multiple peaks, which we will come back to, are due to the occurrence of isotopes in nature. Most likely these additional peaks are due to the occurrence of carbon-13, it's about 1.1%, and in the middle we might hypothesize that another heteroatom is in this molecule, for example bromine, but we do not know this yet. So if you look at a mass spectrum like this, you cannot immediately and easily interpret it. You need to have some knowledge and you need to have some software. So how can we get the sample into the mass spectrometer? There are a couple of principal ways. The first is liquid chromatography. This is a very powerful combination, as we can separate molecules in a complex sample first, for example by reverse phase chromatography based on the hydrophobic properties, and then introduce them into the mass spectrometer one after the other. While liquid chromatography is a very powerful separation technique, it is generally not sufficient to separate each and every molecule in a complex biological sample such as blood, serum or urine, as there may be hundreds of thousands, maybe a million molecules. Nevertheless, liquid chromatography mass spectrometry is to date the most powerful combination of separation and analysis techniques for complex samples. Laser desorption, we will hear about that. We can introduce molecules into a mass spectrometer by shooting a laser at a crystalline sample. This sample will absorb light, and thus, due to the energy of the laser, ions will be formed. Direct infusion is kind of a simple version compared to liquid chromatography. Here we have the sample, for example, in a syringe pump, and this sample is continuously infused into the mass spectrometer. This can be very helpful, for example, for calibrating the instrument with known compounds of defined mass, as we may need some time for accurate calibration. This is done from time to time to either recalibrate the instrument or to check whether the calibration is still in order. Finally, and originally used, gas chromatography can be used. Gas chromatography is ideally suited to combine with mass spectrometry, as the molecules are already in the gas phase. They just have to be ionized to be introduced and analyzed by a mass spectrometer. Unfortunately, most biological molecules cannot be transferred into the gas phase without breaking them. Some can be derivatized, as we heard from the work of Anderson. You could methylate amino acids. You can perfluoromethylate sugars, but this requires chemical derivatization. That's why most of these molecules to date are analyzed by liquid chromatography mass spectrometry rather than gas chromatography mass spectrometry. However, there are quite a few molecules, for example in the petroleum industry as we heard about, but also others that are very suitable for gas chromatography mass spectrometry, and this is then also the method of choice. There are a number of possibilities to ionize molecules for mass spectrometry. Electrospray ionization is very important for molecules in the liquid phase, such after liquid chromatography. It's also very important for biological macromolecules such as proteins, since it is a soft ionization technique and it will not, or to a little extent, break the molecules during ionization. We will hear more details about this ionization technique in a minute. Atmospheric pressure chemical ionization is a more harsh method, especially used for molecules that do not have ionizable groups. It's abbreviated APCI. In this case, a plasma is generated in which ions are formed even of molecules that do not ionize easily. As you may imagine, if you have a discharged plasma, biological molecules are likely not to survive this process. Matrix-assisted laser desorption ionization is another soft ionization method with which macromolecules can be ionized. It is principally different from the other two, as ions are generated from the solid phase and not from the liquid phase. We will also hear more about this ionization technique later on. There are more ionization techniques, especially for gas chromatography, mass spectrometry, like electron impact, where an electron beam is directed at the molecules. We will not deal with those, as those are not so relevant for large biological molecules and also for smaller molecules like metabolites. Chemical ionization is a derivative of electron impact. Electrons are then first directed at a chemical molecule like methane. Methane is in turn ionized and then transfers an electron, for example, to the molecule that should be ionized. In that sense, it's a bit comparable to APCI, as this is a kind of indirect ionization method. It's more soft than electron impact. In electron impact, the molecule is usually broken up into fragments, where in chemical ionization the molecular ion is usually still present. Finally, we have photoionization. Instead of shooting electrons at the molecules, you can shoot photons at them with a high-intensity lamp. These photons can be absorbed by certain molecules, if they have chromophores, and then, due to the absorption of high-energy photons, molecules will be ionized. We will not deal with this ionization method in this course either, as it is also not used very much for biological molecules. Let's take a look at electrospray ionization. Imagine a sample solution, for example, coming out of a chromatography column, enters a capillary, and this capillary goes into the mass spectrometer. At the end of this usually stainless steel capillary, a strong electric field of about 3000 volts is applied between the end plate, which you see as a black vertical line, and the end of the capillary. As you can see, the liquid is drawn out by this strong electric force, and positively charged ions are enriched at the tip, because they would like to go to the negatively charged end plate. In this case, this is positive electrospray ionization, or ESI+, where the end plate is negative and positive ions are expelled from this liquid, essentially. For certain solutions, and especially at higher flow rate, it is necessary to help this ionization process with a nebulizing gas which flows parallel to the stream of liquid. This nebulizing gas essentially makes a jet and then helps the ionization and also the evaporation of the solvent. As there's lots of solvent coming out of a chromatography column relative to the high vacuum needs of a mass spectrometer, we need some help to evaporate this solvent. This is generally done with a so-called drying gas. Most of the time this is nitrogen that is heated to maybe 200 or 300 degrees, or maybe even more, to quickly evaporate, for example, methanol, water, and formic acid, which are typical components of reversed phase liquid chromatography. Let's take a look at what might be happening to such a droplet. Droplets are pulled out of the tip of the capillary as shown before, and in the beginning, depending on the diameter of the capillary, they may have a radius of 1 micrometer. This is fairly big compared to an ion, so there are many positively charged ions on the outside of the droplet that would like to go to the oppositely charged end plate. As the droplet dries under the influence of the drying gas, its radius shrinks. So the positive charges are squeezed together. At some point, the repulsion between these positive charges is so strong that they essentially explode the droplet. This is called the so-called Rayleigh limit, a limit where the repulsion between the ions counteracts and exceeds the surface tension of the droplet. So you end up with many offspring droplets, in this case of about 100 nanometer radius. Again, evaporation takes place and another explosion happens, generating smaller droplets of, let's say, 10 nanometers. At the end, all the solvent is gone and only gas phase ions are left. Thus you have transferred ions in the liquid phase, for example proteins on the upper left, into ions in the gas phase amenable to mass spectrometry. Let's look at the electrospray ionization mass spectrum of a small molecule, Vecuronium bromide. There are some interesting features in this spectrum. First of all, we see two signals, two principal signals for one molecule. How can this be? This is a specific of electrospray ionization mass spectrometry. Due to the process of ionization, as we've seen before, multiple charges can be, in a way, squeezed onto the molecule. At 557, we see the molecular ion of the molecule. If we take a look at the right side, this positive charge is localized at the quaternary ammonium group on the right. At 279, we see a doubly charged ion. This ion contains the original positive charge plus a proton that was transferred, for example, from the acid in the solvent, usually formic acid, to the molecule during the ionization process. I assume that this positive charge sits at the other nitrogen atom on the left side. What we further see is that this is not a single peak. We see at 279 two peaks, if we look carefully, close together, and at 557 we may even discern 3 peaks. As mentioned before, these multiple peaks per ion are due to isotopes, and in this case they are due to the occurrence of carbon-13 in nature. In a few minutes we'll spend a few minutes to look into isotopes and how they affect a mass spectrum. As already mentioned, electrospray ionization mass spectrometry leads to multiply charged molecules. This is very prominent for macromolecules such as proteins. Let's look at myoglobin here, a molecule with 16,950 Dalton molecular weight. This is a spectrum of only myoglobin, but we see many peaks. These peaks are due to different charge states of the same molecule. And the charge states are due to protons being attached to the molecule during the ionization process. We see the highest peak has 15 protons on it. The next one left to it 16 protons, 17 and so on. And to the right side the charge state goes down, 14 proton, 13 protons. Remember, a mass analyzer measures mass to charge ratio. So while the mass of myoglobin is always the same, the charge state changes and thus the m/z changes. This leads to multiple peaks. Originally, this was considered a big disadvantage of electrospray ionization mass spectroscopy because it leads to very complicated mass spectra. Imagine, if one molecule already gives 10 peaks, what would happen if you had 1,000 molecules in a sample? It would not be possible anymore to discern which peak belongs to which molecule. However, fortunately, we have liquid chromatography to separate molecules, and fortunately, not every molecule acquires as many charges as myoglobin. On the other hand, there's a big advantage to it too. You have now, instead of 1, 10 measures of the molecular mass of myoglobin. So with a simple algorithm you can now calculate an average molecular mass and a standard deviation. And so your mass measurement becomes much more accurate than based on a single peak. I've already referred to isotopes a couple of times, so let's take a look more closely at isotopes with different elements and how they affect the mass spectrum. Which isotopes should we be concerned about? First and foremost we have the carbon isotopes 12 and 13 nominal mass. Especially carbon-13 is very important for mass spectrometry, as it leads to the multiple peaks that we've already seen. Further to this, the presence of carbon-13 in molecules in nature is also very advantageous for interpreting mass spectra, as we will see in a minute. The exact mass of carbon-13 is 13.00335. As you know, the isotope 12 of carbon, the main isotope, has been defined to have the exact mass of 12.0 and forms the basis of the molecular mass scale. The C12 isotope is present in 98.9%, and 1.1% of all carbon in the world are constituted of carbon-13. This gives an average mass for carbon of 12.01115. Look at the other isotopes. We have hydrogen with its heavy isotope deuterium. This is twice as heavy. Exchange of hydrogen for deuterium is often used to generate internal standards for mass spectrometry. as they have about the same physico-chemical properties but differ significantly in mass, though these are ideal to normalize and correct the intensity and mass spectra and to translate them into concentrations, for example. There's only 0.02% of deuterium in nature, so it's a very minor isotope. It's about similar for oxygen, where we have O16 and the stable isotope O18. We have 0.20% of that. For nitrogen we have the main isotopes N14 and the stable isotope N15 at 0.37%. And finally sulfur. It's a bit more complex. It has 3 isotopes that are relevant, 32 the main one, 33 and 34, with the percentages given on the right, 0.76% for S33 and 4.22% for S34. But after all, the most abundant element in organic molecules and in biological molecules is carbon. So let's focus on carbon-13 to explain how isotopes affect mass spectra. To this end, let's look at a very simple scheme. This is a molecule of 10 by 10 carbon atoms. That means this molecule has 100 carbon atoms. This is not unusual, for example, for a somewhat medium-sized peptide. Out of 100, there's a chance that one of these 100 is carbon-13, because we have 1.1% of carbon-13 in nature. This is, however, a completely stochastic random process. I cannot tell which of these 100 is carbon-13, but there is a high statistical probability that one is. Now, with mass spectrometry or most other analytical techniques, we're not looking at single molecules, but we're looking at an ensemble of many, many molecules. So that means, averaging out, we will find 1.1% of all carbons in molecules being carbon-13. So the blue spots are carbon-12, and the red one is the one carbon-13 atom in this molecule. And these are the natural abundances again, 98.9% for C12 and 1.1% for 13C. Now let's look at a mass spectrum of a peptide, angiotensin 1, which is related to blood pressure regulation. Angiotensin 1 contains 62 carbon atoms, 90 hydrogen atoms, 17 nitrogen atoms, and 14 oxygen atoms. The main peaks that we see for this molecule, angiotensin 1, and this spectrum is all just this one molecule, the MH plus ion. We see on the left a peak at 100%, then spaced by 1 atomic mass unit to the right. We see the first peak with 1 carbon-13, the next one has 2 carbon-13s, 3 carbon-13s and 4 carbon-13s. And the intensity of these peaks simply reflects the statistical probability that there is 1 carbon-13, that there are 2 carbon-13s in a molecule, 3 or 4 in the same molecule. This gives the so-called isotopic envelope. Why is that so interesting for mass spectrometry? Now we can define different mass values. The most left, biggest peak, is the so-called monoisotopic mass, 1296.69. We can now define this mass with very, very high accuracy, because we're only looking at the C12 isotopes. You might say, so what about the hydrogen, nitrogen and oxygen isotopes? Yes, they are also present, but they are not visible in this mass spectrum. You would have to zoom into the background noise, because remember, carbon-13 is 1.1%, while hydrogen, or deuterium I should say, is only 0.02%. You will see this fine structure with very high resolution mass analyzers if you zoom into the baseline, but for the most practical purposes of bioanalysis we are only concerned with the carbon-13 isotope pattern. If you want to play around a little bit with different compositions and how the isotope patterns look like, here's a link to the ChemCalc algorithm which allows you to do that. Let's look at the mass spectrum from our own work. Here we see 3 major peaks. However, the difference between the peaks is 0.5 instead of 1. However, the mass difference between C12 and C13 is 1 atomic mass unit. So how is it possible that the distance here is 0.5? Well, let's go back to basic. A mass analyzer does not measure mass, but it measures the mass to charge ratio. So this simply means that this ion is doubly charged, because it's C13 minus C12, which is a difference of 1, divided by 2, the 2 charges C, which gives 0.5. This already shows you clearly that looking at the isotope pattern is an excellent means of determining the charge state of the molecule. On the left side you see the all C12 monoisotopic mass, and you see the next peak contains 1 carbon-13. So dependent on the resolution of your mass analyzer, because these isotopic peaks must be resolved, you can actually determine the charge state of a molecule. Modern acquisition software of mass spectrometers can do this automatically on the fly and use this information to calculate the molecular mass of an ion. Here we see another peptide mass spectrum. Again, as you can see, the difference is 0.5, so this is another doubly charged ion. So what about this one, another mass spectrum of a peptide? Here we see a difference of 0.33 or 0.34. As you can see, the third peak was not really acquired at the top, but that is typical of mass spectrometry because mass spectra are acquired at a certain rate, so it may not just hit the top of the peak in this case. Anyway, the difference is 0.33, so what is then the charge state of this ion? It's simple. 1 divided by 0.33 or 1 divided by 1/3 means that the charge state is 3. This finishes our short intermezzo about isotopes. Remember why there is an isotope fine structure, mainly due to the presence of carbon-13 in nature. And importantly, remember how the distance between the isotopic peaks can lead you to determining the charge state of the ion, which is essential to calculating the correct molecular mass. We've discussed electrospray ionization, ESI, as a soft ionization technique to transport molecules from the liquid into the gas phase. Now we're going to look at 2 other important ionization techniques. First of all, matrix-assisted laser desorption ionization, also called MALDI. This ionization technique transfers ions from the solid state into the gas state under the impact of a laser. Finally, we'll take a brief look at atmospheric pressure chemical ionization, APCI, which is useful for molecules that do not contain ionizable groups. As said, MALDI transfers ions from the solid to the gaseous state. To this end, samples are deposited on a so-called target plate as shown in this slide. A target plate essentially allows to crystallize a small volume like 1 microliter of matrix and sample and let it dry and then ready for laser irradiation. As you can see, there are many little places on such a plate, so MALDI is a fairly high throughput methodology. You can deposit hundreds of samples on a single target plate, and then the laser will scan over the different deposits and produce mass spectra for each and every sample. As indicated by the name matrix-assisted laser desorption ionization, there is a need for a matrix to help in the ionization. Matrix molecules have two principal characteristics. One is an aromatic system to absorb the laser light, and second, a carboxylic acid group to help in the ionization by transferring a proton. Let's look at a few examples of matrices, of which there are many. Nicotinic acid has the typical properties. It has a pyridine ring and a carboxylic acid. It's a very simple molecule. It absorbs light at 266 nanometers and is used for proteins. However, not very widely, because the wavelength is fairly short and you would need a UV laser. Most lasers to date in mass spectrometers are nitrogen ion lasers emitting around 337 nanometers. For these lasers, 2,5-dihydroxybenzoic acid and alpha-cyano-4-hydroxycinnamic acid are widely used matrices. Especially the so-called alpha-cyano is used for peptides and proteins, while 2,5-DHB is more widely used for carbohydrates. Cinnapinic acid is also used for peptides and proteins. It contains another double bond to have a conjugation with the aromatic system, as does alpha-cyano. And at the bottom we have ferulic acid. You can see while there's a wide variety of matrices, they are structurally all very similar because of the requirements to absorb the laser light and to transfer protons. Looking at a schematic of MALDI, we see that on the target plate, so this is one of these round things that we saw before, we see the matrix, so a lot of matrix, and a few analyte molecules embedded in the matrix. You can imagine as the laser pulse hits, a lot of energy is transferred to the matrix. This leads to kind of an explosion and a very hot plasma above the target plate. In this plasma, ions are generated through ionization directly through the light, but mainly through proton transfer from the matrix. Ions are then accelerated in a very strong electric field of about 20,000 volt into the time-of-flight mass analyzer, about which we will hear in a few moments. Let's finish this section on ionization techniques with atmospheric pressure chemical ionization, or APCI. It's again a method to ionize molecules from the liquid phase. It can thus be very nicely coupled to liquid chromatography. For molecules that do not ionize easily with electrospray, it is possible to support this process with a corona discharge electrode, which is placed behind the capillary. In a corona discharge electrode, something happens like in a lightning when there is a thunderstorm. High energy is transmitted and ions are generated. These ions are then accelerated into the mass spectrometer by a strong electric field. As you can see, the rest of the interface is pretty much similar. You have the drying gas to evaporate the solvent, and you have the hole, the skimmer in this case, to transport the ions in the gas phase to the high vacuum of the mass analyzer. You can also have a nebulizer gas, especially for higher flow-through liquid chromatography. The reactions happening during atmospheric pressure chemical ionization, APCI, are quite complex. They are, as I said, somewhat comparable to what's happening in a lightning. For example, molecular nitrogen, a fairly inert molecule, can be ionized. It can transfer charge to water, and water in turn can transfer a proton to the molecule M, generating positively charged Mh+. Don't worry about the details here, but remember that inert molecules are activated to ionize your analyte molecule. The analyte may also be negatively charged by absorbing an electron that forms a negatively charged radical anion. Also, reactions between molecules and electrons can lead to dissociation into a radical and a negatively charged anion. And this energetic species can again abstract the proton from another molecule and ionize it. So it's kind of a chain reaction that's happening to try to ionize molecules that usually do not have ionizable groups. The second and maybe most central part of the mass spectrometer is the mass analyzer, which effectuates the mass-to-charge ratio separation of ions in the gas phase. There are a couple of mass analyzers ranging from low resolution to very high resolution mass analyzers. Most widely used is the Quadrupole. It's now considered to be a low to medium resolution mass analyzer with a resolution of about 1000 to 2000. The Quadrupole can be used as a quadrupole as such, as a transmission quadrupole, as well as a quadrupole ion trap, either three-dimensional or linear. In that case, ions are trapped within the quadrupole and accumulated and then scanned out according to their mass-to-charge ratio. We'll see more about that later on. The next mass analyzer we've already heard about a little bit is the time-of-flight mass analyzer. This is an analyzer that simply measures the time of flight of an ion from the entry of a flight tube to the detector. This time of flight, as we will see, is related to the mass-to-charge ratio. The time of flight mass analyzers with modern improvements can reach up to 50,000 resolution and is considered a semi-high resolution mass analyzer. The more recently developed Fourier transform Orbitrap is a trap analyzer where ions are again trapped but oscillate along a bottle-shaped central electrode, which we will see in a few minutes. The Orbitrap, as a Fourier transform system, can reach resolutions between 30,000 and 50,000, depending on the mass-to-charge ratio and also depending on the accumulation time. Because the longer you accumulate in a Fourier transform system, the higher the resolution you can reach. That means you have to find a compromise between data points per time and resolution. The last mass analyzer is the Fourier transform ion cyclotron resonance mass analyzer. We will not deal with that in great detail as it is barely used in bioanalysis. This mass analyzer, which was developed already more than 30 years ago, can reach resolutions of more than 1 million and is thus the highest resolution mass analyzer. However, it requires a superconducting magnet which has to be cooled with liquid helium. This already shows to you that this is far from a routine mass analyzer. Let's take a look at the Quadrupole mass analyzer. It is a fairly simple device, as you can see. It has 4 rods, thus the name Quadrupole, 4 electrical poles. In this figure, 2 poles are negatively charged and 2 are positively charged. Imagine now a positively charged ion coming out of the ion source at the bottom and entering the Quadrupole mass analyzer. This positive ion will be attracted to the negative poles, and if nothing else happens, it will hit this pole and will be decharged and lost. However, the Quadrupole is switched on and off and the poles are changed between positive and negative with a certain frequency cosinus omega t, so-called radio frequency. If this frequency is resonant with the ion, then as the ion approaches the negative poles, these will become positive and the positive poles will become negative. As this is switched back and forth at the proper frequency, the ion will oscillate through the Quadrupole and reach the detector. However, every ion has its own proper resonant frequency. So if the frequency RF is not in resonance with the ion will be lost either against the oppositely charged poles or the other poles. In order to transmit ions over a range of mass-to-charge ratios, the radio frequency can be programmed to change. This is called a scan. For example, the frequency can go from high frequencies, which are appropriate for ions with low inertia, this means with low mass, to a slower frequency, which is more appropriate for heavy ions. As you can imagine, inertia plays an important role because the ions have to change their way of movement according to the frequency. Light ions can move fast because they have a low inertia. Big ions move slowly and thus require a longer resonant frequency. Modern quadrupole mass analyzers can scan very fast, certainly multiple scans per second. Another frequent application of the quadrupole mass analyzer is that of a mass filter. For example, if you know exactly which ion you would like to analyze, and as we'll see later, fragment and find out more about it in terms of structure, you can set a fixed radio frequency that is only appropriate for this ion. Then all other ions will be filtered out and only the one ion will go through the detector. A very widely used setup is the triple quadrupole mass analyzer. As the name indicates, it consists of 3 quadrupoles in a row. You see on the left quadrupole number 1 or Q1. This can be used, for example, as a mass filter as shown in this slide. Many ions of different mass to charge ratio enter on the left side, while only one ion, plus, comes out on the right side. This means that the radio frequency was set in resonance with this ion. You can now direct this ion into the second quadrupole Q2, which is used as a collision cell. Here the ions collide with inert gas molecules such as nitrogen or argon. In that case, the ions break into fragments. These fragments are subsequently analyzed by quadrupole mass separator number 3. This quadrupole is scanned over a certain M/C range, and then the ions enter the detector to provide signals. Triple quadrupole mass analyzers can be used in different ways and are very frequently used in bioanalysis, as we will see later on. In this case, the use is to gain structural information about the ion that passes the first Q1 filter by looking at its fragments that are analyzed in quadrupole Q3. We've already heard about matrix-assisted laser desorption ionization, or MALDI. Just to remind you, this is a pulsed laser technique, which is very important to connect it to the following mass analyzer. This is discrete ionization packages are evaporated by the laser pulse at somewhat 100 or even 1000 Hertz. That means 1000 laser shots per second. This is ideally coupled to the time of flight or TOF mass analyzer. The source on the top is thus the MALDI source, where ion packages are generated. These ion packages are accelerated in a strong electric field of about 20,000 volts through a hole into a completely empty tube, the so-called flight tube. This tube has a very high vacuum of 10 to the minus 10 torr and a fixed length. It is also a field-free flight tube. That means there should be no electrical or magnetic fields that could deviate the ions. Essentially, there should be no effect on the flight of the ions by collisions or external fields. If that is the case, ions will take a certain time to reach the detector. This time is called the time of flight. How is this time of flight now related to the mass-to-charge ratio? Take a look at the right side of this slide. Each ion acquires a certain kinetic energy based on the acceleration in the electric field. This kinetic energy is equal to Z, which is the charge state, E is the elemental charge, and V the voltage that's applied. On the left side you see that the kinetic energy is 1/2 the mass times the square of the velocity, a well-known equation. We can now replace the flight time t equaling the length divided by the velocity. Sorry, rather the other way around. We can replace the velocity up there by flight time t. So if we put v equals L divided by t, and we resolve this equation to the mass to charge ratio, then we will see it is related to the square of the flight time. The elemental charge, the voltage which was set on the instrument, and the length of the flight tube are all constants. So mass to charge is proportional to the square of the flight time. This is the simplest version of the time of flight mass analyzer. As we will see later, some improvements have been made to increase the resolution. However, this is the basic relationship between time of flight and mass to charge ratio. Possibly the most important improvement of the time of flight mass analyzer was the Reflectron. Why do you need a Reflectron to get high resolution in a time of flight mass analyzer? The reason is that the initial kinetic energy of ions is not exactly the same. This can be easily understood if you imagine a laser hitting the target and generating a cloud of ions at high energy. Not all the ions are at the same place, so the acceleration voltage will be slightly different for these different ions due to the different distances to the opposite charge plate. As an ion enters through the hole with slightly different velocities, but the same mass to charge ratio, it will have different inertias. The Reflectron is simply a series of plates with the same charge, in this case positive, of increasing electric field. So as the ion approaches the Reflectron, a slow ion of m/c will only dive in a little bit into the Reflectron before it is deflected back to the detector. An ion with the same m/c but higher velocity will dive deeper into the Reflectron. It will have to travel a longer distance, and the Reflectron is optimized to refocus these ions coming out at the same time and hitting the detector at the same time. In a way, it's an ion refocusing device. Thanks to the Reflectron and a couple of other improvements of the time of flight mass analyzer, these instruments can now reach resolutions of up to 50,000 or sometimes even more. Different mass analyzers can be combined in so-called hybrid instruments. Here we see a very common combination of a quadrupole mass analyzer and a time of flight mass analyzer. You may ask, how is this possible? The quadrupole mass analyzer works in this case with an electrospray ionization source. On the left side you may imagine the HPLC system. This is a source that generates ions continuously, while the time of flight mass analyzer requires ion packages to measure their time of flight. Let's see how this combination is brought about. In this instrument, the so-called QTOF, quadrupole time of flight instrument, ions are first focused and pass through Q1, the first quadrupole, that can be used again as an ion filter. They pass through Q2, which is again the collision cell where fragments can be generated. Then ions are focused again and reach the time of flight mass analyzer. Here we have a so-called pusher region. Ions are collected for a certain time and then are pushed by very strong and fast nanosecond electric pulse into the time of flight analyzer. In this way, a continuous beam of ions can be cut up into ion packages. The time of flight of each of these ion packages is measured, and as you can see, the instrument, as most instruments to date, contains a Reflectron, and then the ions reach the detector. What is the advantage of such a combination? Main advantage is that you can do a standard quadrupole type of experiment in the beginning, selecting ions, fragmenting them, but then getting very high resolution and accurate mass measurements of the fragments. This helps especially in complex samples like proteomics or metabolomics samples, where you have many compounds and you would like to A, measure them accurately without interference by other ions, and second, sometimes you would like to identify them, so you need high mass accuracy for the identification. This is a schematic of the quadrupole ion trap mass analyzer. It is in principle a quadrupole, but not linear but three-dimensional, enclosing a space. As ions enter from an atmospheric pressure ion source, for example an electrospray ionization source, they are collected in the ion trap up to a certain number, for example 50,000 ions per cycle. They can then be scanned out by changing the radio frequency again to get an overview spectrum, a so-called MS1 spectrum. In a second step, an ion of interest can be isolated in the ion trap and then scanned out to make sure you have the correct ion, M+. What is very powerful in an ion trap, that now selected ions can be excited to collide with helium, which is in the ion trap at a low pressure, and be fragmented. So you can now fragment ions at different energies and get fragments that can be scanned out and get an MS2 or fragment ion spectrum or product ion spectrum. This allows you to isolate ions one after the other, fragment them, and gain fragmentation or structural information. The ion trap is thus a tandem mass spectrometer, as we call it, in time, because the events happen one after the other. A triple quadrupole or QTOF mass analyzer is a mass spectrometer that is tandem in space, because the mass analyzers are separated in space and one thing happens after the other in space. While only introduced in 2004, the Fourier transform Orbitrap mass analyzer has gained considerable popularity in the last 10 years. Many instruments have been sold despite the fairly high price. Why is that? The mass analyzer is fairly small, making this a benchtop instrument, but with the resolution of the much bigger and more difficult to use ion cyclotron resonance mass analyzer. It's thus a very high resolution mass analyzer that can be used in regular bioanalytical laboratories. It's still mostly in research instruments, but it's finding its way more and more also in routine laboratories. For example, here at the University Hospital Pharmacy. How does it work? It's an ingenious invention actually. As you can see, ions are injected from the top around a bottle-shaped electrode along the z-axis. Ions are not injected right in the middle, but a little bit off-axis. Thus they experience an electric field that makes them oscillate along the z-axis. Heavier ions oscillate more slowly than lighter ions. As they oscillate, they induce a current in the electrodes around them, and this current is kind of a music that the ions play. These frequencies are then Fourier transformed and then translated into the mass-to-charge domain after calibration of the mass analyzer. Depending on the time that you allow the ions to oscillate and thus the electrode to acquire the music, the resolution is higher or lower. The longer you wait, the higher the resolution. The shorter, the faster you want to measure, the lower the resolution. But even for fairly fast measurement cycles, resolutions are still on the order of 50,000, while they can reach up to 1 million if you give it enough time. The frequency that you get is related to the charge-to-mass ratio according to the equation at the bottom left. There's an instrument-related constant which is connected to the dimensions of the Orbitrap. Otherwise, the relation is fairly simple, as the frequency is just equal to the square root of z divided by m. Also, Orbitrap mass analyzers have in recent years been combined with quadrupoles before. So instead of having a QTOF, you have a Q-Orbitrap mass analyzer, meaning a quadrupole, a collision cell, and then an Orbitrap instead of a TOF mass analyzer. Such instruments are available also in our laboratory. I've often referred to resolution of a mass analyzer so far, but how is resolution defined? There are actually a couple of definitions in the literature. I'll just show you one to give you a general idea. Look for example at this peak at 500 mass-to-charge ratio or atomic mass units. This peak has a peak width at half height of 0.7 units. The resolution is thus 500 divided by 0.7, which is 714. This is a low resolution mass analyzer, even for a quadrupole. Imagine a high resolution mass analyzer. This would give you a much sharper peak, and thus delta M, as delta M goes down, gets smaller, the resolution goes up. Calculate for yourself what the peak width would be for a resolution of 10,000. Why is resolution so important? Let's look at these three mass spectra. The top one is taken at a resolution of 3000, which is typical for a quadrupole at a fairly slow scan speed. You can see the isotopic peaks, but they are not fully resolved. The monoisotopic peak is between 1978 and 1980. With resolution of 10,000 in a time-of-flight mass analyzer, the isotopic peaks can be fully resolved and thus the mass measured with more accuracy. If we use an Orbitrap mass analyzer, the resolution at 60,000 gives very sharp peaks and plenty of space in between. So the peaks can be easily resolved, and even molecules of higher mass-to-charge ratios can be resolved, or of higher charge states. Let's look at two examples showing why resolution is so important, especially for the analysis of macromolecules. Here we have two proteins, a biomarker, insulin-like growth factor 1, which is related to growth hormone-related disorders, and a monoclonal antibody, the most important class of biotherapeutics to date. Insulin-like growth factor contains 331 carbon atoms, 518 hydrogen, 94 nitrogen, 101 oxygen and 7 sulfurs. The monoclonal antibody, which is much bigger, contains 6,560 carbons, 10,132 hydrogens, 1,728 nitrogen, 2,090 oxygen and 44 sulfur. Enter these formulas into the ChemCalc.org calculator and look which resolution you would need for your mass analyzer to separate the isotopic peaks. To identify molecules by high-resolution mass spectrometry, we have to work with the exact or accurate mass based on the monoisotopic peak. Remember the peak on the leftmost side of the isotopic envelope. The average mass is no good for this, as it deviates significantly from the accurate mass. The average mass averages over all the isotopic peaks. For a small molecule like amphetamine, this difference is relatively small, but already significant. As the molecules get bigger to angiotensin 1, you see that you have almost 1 atomic mass unit difference. For insulin-like growth factor 1, this difference has increased to almost 5 atomic mass units, and for a monoclonal antibody, it is even much bigger. Thus remember, for high-resolution mass spectrometry, you have to measure the exact or accurate mass, so you have to look at the monoisotopic most leftward peak. Here is a measurement, an example from the lab. The small protein cytochrome C of 12,500 Dalton is measured at a resolution of 100,000 in our Orbitrap mass analyzer. On the top you see the overview spectrum with the different charge states as generated by electrospray ionization. Let's zoom in on the middle most abundant charge state and blow it up. There you can see the exquisite resolution of the mass analyzer. You can see the different isotopic peaks being separated. As the delta mass to charge is 0.0715, we can see that the charge state is 14 plus. Remember the intermezzo with isotopes and determining the charge state. There we looked at charge states of 2 and 3, which was quite easy. But for bigger proteins, as you already saw for myoglobin, charge states can be much higher. So it's very important and very beneficial to have a very high mass resolution mass analyzer. Very high mass resolution can help to reduce background noise in bioanalysis. As biological samples are very complex, there are often molecules that have highly similar mass-to-charge ratios and that can interfere, as in this case, with an LC-MS analysis of Salmon calcitonin. In this chromatogram, we see the analysis at quadrupole resolution, as we call it, plus minus 0.5 atomic mass units. As you can see, there's considerable noise next to the calcitonin peak. If we analyze the same data at higher resolution, 0.05 atomic mass units, you can see that the noise is significantly reduced, as we very specifically capture one of the isotopic peaks. However, please be aware that it can be very critical to exactly have the instrument calibrated, because otherwise you might select next to this peak. Then go to very high resolution, 0.005 atomic mass units. We only select part of this monoisotopic peak, and the background noise is almost completely suppressed. This is a new way of analyzing biological samples, thanks to the availability of ultra-high mass resolution analyzers. Actually, this work was done with an ultra-high resolution time-of-flight mass analyzers, so you can see that the time-of-flight mass analyzers rival the Orbitrap mass analyzers in the latest generation. Summarizing, you heard about the history of mass spectrometry, isotopes and charge states, and how the distance between isotopic peaks can be used to determine the charge state, provided the resolution of the mass analyzer is high enough. You heard about ionization methods, important for coupling to liquid chromatography, such as electrospray ionization and atmospheric pressure chemical ionization. You heard about matrix-assisted laser desorption ionization, or MALDI, which is very important for macromolecules and can be ideally combined with a time-of-flight mass analyzer. On the mass analyzer side, you heard about the quadrupole, as a transmission quadrupole, and as an ion trap. The time-of-flight mass analyzer, including the Reflectron, and the Orbitrap mass analyzer.